All right, hi everybody. Today we are going to talk about dynamic signals, how sensors change their response over time. Sometimes we're lucky enough that we can ignore this completely, but sometimes you really have to reckon with it. So the question with dynamic measurements is, how does a sensor's output respond to a sudden change? So if we instantaneously change the input to the sensor, does the output change instantaneously? In things like calibration experiments that we've seen already, we generally just wait long enough for a steady state answer. So that's one option, if you can do it, is to just be patient until everything comes to a steady state. But sometimes the sensor is slow relative to the system or that you're trying to measure, or the time that you need the information. So if that is a factor, you really need to know so that you can compensate for it or select the appropriate sensor. So it's important to understand the time response of your system. So we like to use math models for the systems and their response, because then we can really accurately predict. So these are all good models to use. Most systems will be something close to this, usually not exact, but close enough to make good predictions. So a zeroth order system, the order refers to the differential equation, the order of the differential equation. So no derivatives is zeroth order. That's just following. So if we change x, the output y changes instantaneously. A first order system has got a first derivative in it. And so that response typically looks like this, exponential growth. And the second order system has a second derivative in it, and it can have the three classic forms for the linear second order equation: overdamped, underdamped, and critically damped. The underdamped case looks something like B here. So a good example of a first order system is a thermometer, because thermodynamic equations are first order systems. Thermometers, if you've ever used a thermometer like this, you poke it into the meat that you're cooking, and it takes a little while to respond. And if you're holding that over a fire, it can be hot. So it's important to know how fast your barbecue thermometer responds if these are what you're designing. Here's a little video example of how all that works.
Casey and I are here in the backyard to talk about how a thermometer response is a first order system. We'll give it a step response of a temperature change and watch how the measurement changes over time. Let's get to the barbecue. Alright, so our initial starting point is around 82 degrees. Let's see what happens when we put it into the meat. Step change. It's approaching steady state. There it is. Way overcooked. Don't eat that meat.
So just as the math behind that response, the first order response is this one. It's a 1 minus an exponential decay. So over time, this goes to 0, and we're left with a steady state value set by this amplitude VA and offset by VO. So here we can see that the temperature in that video started at around 84 degrees. When we plunge the thermometer into the meat, the input instantaneously rises, but it takes some time for the thermometer to respond. By a few seconds, we're up here, pretty much the steady state. So we have several constants that determine the shape of this, the initial temperature VO, the change in temperature VA, so VO plus VA is going up to 211 from 84. So VA isn't 211, it's 211 minus 84, that's the change. And the final state, the time constant tau is the critical thing for a sensor. That's how fast the system responds, and its units are seconds. So in one time constant, the change from here to here, we reach 63%. That's 1 minus e to the negative 1, because we have t over tau up here. So in one time constant, we have negative tau over tau, e to the negative 1 in that equation. So 63.2%. So at one time constant, we're 63% of the way there. By 5 time constants, we're 99.3. So steady state to some significant figures anyway. So the time constant is the critical thing. Our time constant for that BBQ thermometer was on the order of a second or so, because by 5 or so seconds we were pretty much there. But we could measure it more accurately by finding when we go through 63% or other fitting techniques. But as a second order example, I'm using this pendulum that is used to measure the wind speed at a beach where people windsurf and kite surf. So this is at Sherman Island County State Park in Rio Vista. And this flap here is hinged right here, and it blows. The wind is coming this way and lifting this thing up. So if there's no wind, it hangs straight down. If it's really windy, it swings higher and higher. So this is a pendulum system, and it's got a load, so we can model the response of this as a second order system. Most mechanical systems that have F equals ma as their governing equations have a second order form because the acceleration is the second derivative of position. So if it's the underdamped response, right, there are 3 different responses, but underdamped is pretty common. It has this look, which looks very complicated, but it's got an exponential decay term and a sinusoid. So it oscillates from the sine and it decays here, and that's all being subtracted from 1. So eventually we reach this steady state value of ye. So it's 2 parameters in the second order system. So first order we need 1 parameter, second order 2. So zeta, the damping ratio, and omega n, the undamped natural frequency, are what are the determining factors in here. I'm going to simulate this with a website, myphysicslab.com, and we'll see how it responds to a gust of wind hitting this pendulum when it's hanging straight down. So here I can input the amplitude of the gust. I'm not sure what the units are on this. It's a canned simulation, but you can see the gust is going to make it tilt this way. So here we're going to turn the gust on. You can watch the response. So this is swinging out to measure the wind. It's a sensor, and you can see the angle here. It has some overshoot, and then it decays down to this steady state value at the end. So all of the parameters in this second order response can be predicted with these 2 numbers. So that's why we like these kinds of models, because if you know 2 numbers, you can really understand how your system works. So the percent overshoot, the settling time, the rise time, all of these things can be calculated with an understanding of these 2 numbers or estimates of those 2 numbers. So that's the dynamic sensor response portion of this class. So the main thing is to understand, is your sensor instantaneous for your purposes? If you're doing, it depends on what you're controlling. So if you're controlling something like a HVAC system in a building, you don't really need fast responses. Your temperature sensor can have quite a big time constant, and it should be fine because the building also has a really big time constant. in fact, and how fast it heats up. But if you're controlling something really active like an anti-lock braking system or a quadcopter drone, you're going to need sensors that have a faster response. So most of the time, the 0th order model, where we just neglect time considerations altogether, works fine. But if not, consider a 1st order model or a 2nd order model, and that will usually get the job done. Okay, hope you enjoyed the video, and I will see you next time.